We'll start in about a minute. Today we'll continue in Chapter 11, Section 2 on infinite series. Remember, there's Test 3 on Friday, and it will be over sections 10.1 through 10.4 and 11.1 and 11.2. Tomorrow and Wednesday we'll review for Test 3. Hey, the next thing to look at in Section 11.2 is the harmonic series. So it's the sum of the terms 1 over n, as n ranges from 1 to infinity. So if you write out the first few terms, it's 1 plus 1/2 plus 1/3 plus 1/4, and so on. So we're going to determine whether the harmonic series converges or diverges. So what do you think? Have you seen the harmonic series before? What do you remember? Does it converge or diverge?
I believe it converges, if I remember correctly, but I might be mistaken.
So did you say converge or diverge?
I believe it might converge, if I remember correctly, but I might be mistaken.
Well, it's a toss-up, flip a coin. But okay, so we're going to determine whether or not it converges or diverges. So I'm going to start with, remember in general what the nth partial sum is. So the nth partial sum, we use S sub n for the nth partial sum. So the partial sum S sub 2 is the sum of the first two terms. So in this case, S sub 2 is 1 plus 1/2. I didn't list S sub 1 for a reason, but S sub 1 is just 1. S sub 2 is 1 plus 1/2. What's S sub 3?
1 plus 1/2 plus 1/3.
Right, 1 plus 1/2 plus 1/3. But I'm going to skip that one and write what S to the 4th is, or S sub 4 is. And that's 1 plus 1/2 plus 1/3 plus 1/4. Then I'm going to jump all the way to S sub 8. That's the sum of the first 8 terms. So this is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. So it gets to be kind of tedious after a while, but I've chosen these for a reason. S sub 2 is 1 plus 1 times 1/2. Notice that S sub 4, 1 plus 1/2 plus 1/3 plus 1/4, is greater than 1 plus 1/2 plus 1/4 plus 1/4. All I did was, instead of writing plus 1/3, I wrote 1/4 in its place. And 1/3 is greater than 1/4, so the fourth partial sum of the harmonic sequence is greater than this. But notice that 1/4 plus 1/4 is 1/2. So this is 1 plus 2 times 1/2. Because I have 1/2 plus 1/2, so 1 plus 2 times 1/2. Okay, then we jump all the way to S sub 8. Well, I usually do this to myself. I usually don't leave enough space to write what I want to write next. But I'll see if I can squeeze it in. The 8th partial sum of the harmonic series is greater than 1 plus 1/2 plus 1/4 plus 1/4. And then for the last 4 terms, I'm going to replace those with 1/8 plus 1/8 plus 1/8 plus 1/8. But what do I have on the right-hand side? I have 1 plus 1/2 plus another 1/2 plus a third 1/2. So below that, I'll just write that S sub 8 is greater than 1 plus 3 times 1/2. So these partial sums that I've chosen, the subscripts are powers of 2. So I could rewrite this S sub 2 as S sub 2 to the first is greater than 1 plus 1 times 1/2. And S sub 2 to the second, that's what S sub 4 is, that's greater than 1 plus 2 times 1/2. And then S sub 8, instead of writing 8, I can write S sub 2 to the third is greater than 1 plus 3 times 1/2. So do you see the pattern that we're forming here? The exponent on 2 is 1, and the multiple of 1/2 is 1 for this one. For the next one, the exponent on 2 is 2, and the scalar multiple of 1/2 is 2. For the third one, the exponent on 2 is 3, and the scalar multiple of 1/2 is 3. So what should I be able to say about S sub 2 to the nth partial sum of the harmonic series? If it follows the same pattern, what should that be greater than?
1 plus n over 2?
Yeah, 1 plus n times 1/2. Okay, so if the 2 to the nth partial sum of the harmonic series is greater than 1 plus n times 1/2, what's going to happen as n approaches infinity?
It's going to keep increasing.
Yeah, it's going to go to infinity. So the limit as n approaches infinity of s sub 2 to the nth should be greater than the limit as n approaches infinity of 1 plus, I'll just write n over 2. But the limit on the right is infinite. So the one on the left should also be infinity. We can't really say infinity is greater than infinity, but you get the idea. This is like a comparison test. Since the terms from this sequence diverge to infinity, and the terms of the sequence on the left are greater than each of the terms on the sequence on the right, then this must also diverge to infinity. So this shows that the harmonic series diverges to infinity. This same argument is given in the textbook. Okay, we have a theorem. Theorem 6 on page 713 in the textbook. If the series of the a sub n terms as n ranges from 1 to infinity is convergent, then the limit of the sequence a sub n as n approaches infinity is equal to 0. Okay, so we'll just do a short proof of this. So remember the sequence of partial sums, S sub n is the sum of the first n terms of the series. So S sub n is the sum from I equals 1 to n of a sub I. If I write out the first two terms, we would write a sub 1 plus a sub 2 plus dot, 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 and then plus a sub n. So S sub n is the sum of the first n terms of the series. And so if the series converges, then so does the sequence of partial sums. We talked about that last time. So since we're given that the series is convergent, we'll just suppose that the limit as n approaches infinity of the sequence of partial sums is equal to s. If it's convergent, then the limit is a finite number. Okay. Notice that S sub n minus S sub n minus 1, what's that? If I subtract the n minus first partial sum from the nth partial sum, what should I be left with? Well, we can write it out. S sub n is a sub 1 plus a sub 2 up to a sub n. And we're going to subtract the n minus first partial sum. So we're going to subtract a sub 1 plus a sub 2 and so on up to a sub n minus 1.
A sub n.
we're gonna be left with a sub n. In the S sub n, the term before a sub n, maybe I should have written that in there, is a sub n minus 1. So when we do the subtraction, the only term that is left is a sub n. Okay, so that means the limit as n approaches infinity of s sub n minus s sub n minus 1, that has to be the limit as n approaches infinity of a sub n, because s sub n minus s sub n minus 1 is a sub n. And the limit of s sub n minus s sub n minus 1, that's equal to the limit as n approaches infinity of s sub n minus the limit as n approaches infinity of s sub n minus 1. And the limit of s sub n as n approaches infinity, we're supposing that to be the finite number s. And what's the limit of s sub n minus 1 as n approaches infinity? It's the same sequence, we're just starting one term before, but n is still going to infinity. So the limit of this one is also s. S minus s equals 0, and that's equal to the limit of the sequence a sub n. That's what we wanted to show. Okay, so just to reiterate, if this series of a sub n terms as n ranges from 1 to infinity, if it's convergent, then the limit of the sequence a sub n is equal to 0. Okay, so this theorem is going to help us in some cases. But there's an important note, and that is that the converse to Theorem 6 is not true in general. So if the limit of a sequence a sub n is equal to 0, then the corresponding series of a sub n may or may not converge. So let's give an example to show this. Find an infinite series that diverges, but whose sequence of terms goes to 0 anyway. Can you think of an example? Okay, I'll give you one. I'll just pull this out of the air. How about the harmonic series? We showed that this diverges, the harmonic series diverges, and the limit as n approaches infinity of the terms 1 over n equals 0. Right, as n approaches infinity, 1 over n approaches 0. So the limit is 0. So that's the classic example to illustrate that the converse of that theorem is not true in general. But we can use the contrapositive to Theorem 6. And this is called the test for divergence on page 713 of the textbook. So this says if the limit of a sub n as n approaches infinity does not exist, or if the limit does exist but does not equal 0, then the corresponding series of the a sub n terms is divergent. So do you know what I mean when I say contrapositive to Theorem 6?
Maybe.
Did you say, excuse me?
Maybe.
Oh, maybe? Okay. Let's just restate Theorem 6. So what does this Theorem 6 say again? Okay, so this says if the series as n ranges from 1 to infinity of a sub n, if this series converges, then the limit of the sequence of the a sub n terms goes to 0. So the contrapositive that is if the limit as n approaches of infinity of a sub n does not equal 0, then the series does not converge. Well, if it doesn't converge, it means it diverges. So a contrapositive to a conditional statement is true if the conditional statement is true. So just one more thing about this. If you have a conditional statement, like if P, then Q, the contrapositive to this is logically equivalent. The contrapositive is if not Q, then not P. Those are logically equivalent. Okay, so we're using that to help us. We have a test for divergence. So once again, the test for divergence, which is just the contrapositive to Theorem 6, if the limit of the a sub n terms does not exist, or if it does exist but does not equal 0, then the series of the a sub n terms is divergent. Okay, so here's an infinite series that we can show diverges by using the test for divergence. The a sub n terms are the natural log of n to the second plus 1 over 2n to the second plus 1. And if we take the limit of a sub n, so that's the limit of the natural log of n to the second plus 1 over 2n to the second plus 1. So remember what we can do. If we're taking the limit as n approaches infinity of the natural log of a function of n, we can write this as the natural log of the limit as n approaches infinity of n squared plus 1 over 2n squared plus 1. And then what's the limit as n approaches infinity of n to the second plus 1 over 2n to the second plus 1?
One half.
Yeah, it's 1/2. And the natural log of 1/2 does not equal 0. So that means by the test for divergence that this series of the natural log of n squared plus 1 over 2n squared plus 1, that means that it diverges. Okay, Theorem 8 shows some of the things that are true about series. If these two series, the series of the a sub n terms and the series of the b sub n terms, if they're both convergent series, and if c is a constant, then the sum of the c times a sub n terms is equal to c times the sum of the a sub n terms. So this is, you can describe that as a distributive property. And then if you have a series of a sub n plus b sub n, then that can be written as the sum of the series of a sub n and the series of b sub n. And also for differences, the series of a sub n minus b sub n is equal to the series of a sub n minus the series of b sub n. So these work the way that we hope that they work, or at least the way I would hope that they would. But remember that we're assuming that the individual series both converge. Okay, let's look at a bunch of examples. Okay, so on this one, suppose the nth partial sum of the series of a sub n terms is s sub n equals 3 plus 5n to the second over n plus n to the second. If the series is convergent, then find its sum. So what do you think? Do you think the series converges or diverges? And if it converges, what does it converge to? So this is a sort of a test to see if we understand fully what an nth partial sum is. Hey, remember what S sub n is in general. It's the sum of the first n terms of the series. And the limit of the partial sums, S sub n, as n approaches infinity, is equal to the series So if the limit of the sequence of partial sums exists as a finite number, then that means the series converges, and it converges to the same number that is the limit of the sequence of partial sums. Okay, so here's the nth term, or the nth partial sum, I should say. It's the nth term of the sequence S sub n. So if we try to find the limit of S sub n, if this limit does not exist, then the series diverges. But if the limit exists as a finite number, then the series converges, and it converges to the same number that is the limit of the sequence of partial sums. Okay, so what about the limit of 3 plus 5 n to the second over n plus n to the second? So one of our techniques for computing limits works really nicely if you have a polynomial in the numerator and a polynomial in the denominator. So the term with the largest exponent in the denominator is n to the second. So if we divide the numerator by n to the second and the denominator by n to the second, or equivalently, if you multiply the numerator by 1 over n to the second and multiply the denominator by 1 over n to the second, either way, we're going to get 3 over n to the second plus 5, and then 1 over n plus 1 in the denominator. Do you see how I got that? Okay, then we just compute the limit. 3 over n to the second goes to 0. 5 is unaffected by what n does. And in the denominator, 1 over n goes to 0, and 1 is unaffected. So this is 0 plus 5 divided by 0 plus 1, or 5. Okay, so the series converges, and moreover, it's equal to 5. So we can write that the series is equal to 5. It's the same value as the limit of the sequence of partial sums. So I'm not sure, but maybe there's a tendency to think of the sequence of partial sums, confusing it with the terms of the series. I don't know, but the sequence of partial sums is the sum of the first n terms of the series. Okay, let's move on to the next example. If the series, as n ranges from 1 to infinity, of 3 times 5 to the negative n is convergent, then find its sum. So do you have any suspicions about this particular series?
Approaches 3.
What?
The one that approaches 3.
It sums to 3? Oh, I don't know either, but I've done it. I just have such a short memory, I can't remember. But this turns out to be a geometric series. So let's rearrange the terms, or write it in a different form. So 5 to the negative n, that's the same as 1 over 5 to the n. So I'm going to think of this as 3 times 1 over 5 to the n, but that's the same as 1/5 to the n. Are we in agreement about that? Okay, to get it in the form that we want, I'm going to take one of the 1/1/5 factors, multiply 3 times 1/5 times 1/5 to the n minus 1. And then this can be written 3 times 1/5 is 3/5 times 1/5 to the n minus 1. So remember the form that the geometric series, the form that it was presented in a couple of days ago? If you have a series as n ranges from 1 to infinity of a times r to the n minus 1. And then if the value of r is between -1 and 1, then it converges. So I'll just make a note of that. If -1 is less than r, which is less than 1, then this series converges to a divided by 1 minus r. Okay, so I rearranged the given series so that it's in this form. And the common ratio 1/5 is between -1 and 1, so that means this will converge. So in this one, the value of a is 3/5 and r is 1/5. So it converges to 3/5 divided by 1 minus 1/5. And then we just do the arithmetic. 3/5 divided by 4/5, which is 3/5 times the reciprocal of 4/5. Oh yeah, now I remember, it converges to 3/4. Yeah, so just be on the lookout for things that are geometric series, but sort of slightly camouflaged. If you just rearrange it, then you can recognize it as a geometric series. Okay, yeah, so geometric series, that's one of the main types of series that we'll look at. And we have some others. Okay, like this one, express the series. This time n starts at 0 and goes to infinity. And the terms are 2 over n plus 1 times n plus 2. We're going to express it as a telescoping sum. Okay, so on this one, we want to use partial fraction decomposition to rewrite 2 over n plus 1 times n plus 2. So we'll start by writing it as a over n plus 1 plus b over n plus 2. And then we want to find the values of a and b. So if we multiply a over n plus 1 by n plus 2 over n plus 1, we'll get a times n plus 2. Do the same with b over n plus 2. Multiply the numerator by n plus 1 and the denominator by n plus 1. We get b times n plus 1 all over the common denominator. Okay, so we're going to get an plus bn, which is a plus b times n, and then 2a plus b, so what has to be true if this is equal to 2 over n plus 1 times n plus 2? A plus b is the coefficient of n, but this doesn't have n, so a plus b must be 0. And 2a plus b has to equal 2. So if a plus b is 0, a is equal to negative b, or b is equal to negative a. And if I replace b with minus a, I get 2a minus a equals 2, so a equals 2. And b is equal to negative 2. Okay, so we'll rewrite the series as 2 over n plus 1 minus 2 over n plus 2. Okay, then when n is 0, we get 2 over 1 minus 2 over 2, which is just 1. So this is when n is 0. And then we add the next term when n is 1. When n is 1, this is 2 over 2, and then minus 2 over 3. So this is the n equals 1, when n equals 1. Then we add the term we get when n is 2. So when n is 2, we get 2 over 2 plus 1, or 2/3. And then minus 2 over 4. I'll just write it as 1/2. So this is the term that comes from n equals 2. Let's just write one more. When n is 3, 2 over 3 plus 1 is 2 over 4, or 1/2. And then minus 2 over 3 plus 2 is minus 2/5. So this is the one when n equals 3. And so on. This is called telescoping because this minus 2 over 2 plus 2 over 2, those cancel each other out. And then the minus 2/3 and the plus 2/3, those cancel each other out. And then the minus 1/2 plus 1/2, those cancel each other out. So if we continue in that fashion, hey, then the nth term is going to be 2 over n plus 1 minus 2 over n plus 2. But the idea is that this term is going to cancel with the one that came before it. And then if you let n go to infinity, well, this is still going, right? So as n goes to infinity, this term goes to 0. And so the only surviving term is the very first one. 2 over 1. Because all of the other ones cancel each other out forever. And these terms are getting closer and closer to 0. Even though they're all getting canceled out, they're still contributing smaller and smaller quantities. So we conclude the series of 2 over n plus 1 times n plus 2 equals 2. So it's just a coincidence that this numerator is 2, so don't count on that being the limit, or the sum, I should say. Yeah, so that's called a telescoping sum. So make sure that you know about those. So geometric series and series involving telescoping sums, that's another kind. Okay, the next example, find the values of x for which the series -4 to the nth times x minus 5 to the nth converges. So what comes to mind when you see the terms? What's that?
A geometric series?
Yeah, I'm thinking geometric because I have 2 terms raised to the power n, and I'm multiplying, so I can rewrite it as -4 times x minus 5 all to the power n, right? Using properties of exponents. Are we all in agreement about that? Hey, let's go ahead and multiply inside the outer parentheses, simplify what's on the inside. So -4x plus 20, I'll just write it as 20 minus 4x to the power n. Okay, so if this is a geometric series, the common ratio, right, if you were to write out the first few terms, you'd get 20 minus 4x to the first plus 20 minus 4x to the second, and so on, right? So what's the common ratio? So if we divide a term in the sequence by the term that comes before it, I should say in a geometric sequence, it's always going to be the same quantity. So we can tell by looking pretty much that the common ratio is just 20 minus 4x, right? Because 20 minus 4x to the second divided by 20 minus 4x to the first is 20 minus 4x. And in order for a geometric series to converge, what must be true about the common ratio? It has to be between -1 and 1, right? So for convergence, -1 must be less than the common ratio 20 minus 4x, which must be less than +1. So we just solve this compound inequality. First, subtract 20 from both sides. I should say from all three parts. Subtract 20 from all three parts. And we'll get negative 21 is less than negative 4x, which is less than negative 19. Then we divide each of the three parts by negative 4, and then switch the inequalities to their opposites whenever you divide an inequality by a negative. So then I'll rearrange it. Negative 19 divided by negative 4 is positive 19/4, but that's going to be the smallest number. So 19 divided by 4 is less than negative 4x divided by negative 4, which is x. And that will be less than negative 21 divided by negative 4, which is positive 21/4. Okay, so we're out of time. Tomorrow we'll start reviewing chapter 10 and the first two sections of chapter 11. But that's all for today.